Welcome. Now we shall be learning some more about the acid gas removal, something we learnt earlier also. So in this case this is a part 2 on the acid gas removal from natural gas. In this we shall be learning about the membrane separation, adsorption separation, use of sulfide scavenger and the low temperature for the removal of the acid gases. So first we come to the membrane separation of the acid gas. Now here we are using the membrane which is organic membrane, some polymeric membrane is there, and the acid gases are CO2 and H2S, and we have several types of membrane which are broadly classified based on their structures as glassy and rubbery. And then we have the one is the polymer used for carbon dioxide removal is the cellulose acetate, polyimide and perfluoropolymer. And let us look at cellulose acetate, which is very commonly used for acid gas removal, and it is the asymmetric membrane we learnt earlier, that is the skin is about 0.5 to 0.1 to 0.5 micron of cellulose acetate, which is kept on a thick layer of porous material, and it has highest selectivity of carbon dioxide over methane, and it is non-reactive to most organic solvents. And then the selectivity over methane goes from 10 to 20, whereas for the H2S this rubbery kind of polymeric materials are there for the membrane. We are using amide block copolymer and their selectivity is 20 to 30% over methane. Now here we are listing the basic parameters, operating parameters which affect the performance of the membrane. Here we have the flow rate, operating temperature and operating pressure. So we find that the flow rate dictates that if we have higher flow rate, then we find that the membrane performance degrades. So for better membrane performance we need to operate at lower flow rate. Then performance is also seen to drop when we operate above the design flow rate, and we need additional modules of the membrane if we have to handle larger flow rates. Then the operating temperature has this kind of effects, that if we increase the operating temperature, it increases permeability, but it decreases the selectivity. So permeability means we shall be getting higher production, but then we will not be able to separate out the various components which is dictated by the selectivity. And if we exceed the operating temperature, maximum operating temperature, we find it may degrade the membrane material, and thereby it can shorten the useful life of the membrane unit. In case of operating pressure, if the operating pressure is high, then both the permeability and the selectivity increases, and if the difference between the pressures on the permeate side and the retentate side is very high, then we find that the net flow through the membrane will increase, but at the same time we have to keep in mind that the membrane can have enough, should have enough mechanical stability to withstand that kind of high pressure difference across it. In case of membrane, we need to pre-treat the gas because the membrane pores may get choked by some particulate matters. So it is required to pre-treat the membrane to reduce the susceptibility of the membranes by degradation in the presence of some impurities. And there can be several types of impurities. Suppose we have some liquid impurity, and this liquid impurity may cause the membrane swelling. The membrane can get swelled, and then it may result in the decreased flux rate and the possible membrane damage. Then we have the presence of some heavier hydrocarbons, and some especially lubricants. What will they do? That they will coat, that means they will cause some kind of fouling over the membrane surface, and if there is fouling or this coating by these heavier hydrocarbons, then the flux will decrease. So the flux decreases means the membrane performance will come down. Then if we have some particulates, what will happen? They will block the pores through which the solutes will pass through, and thereby they will degrade the performance of the membrane, and if there are any kind of corrosion inhibitors and well additives, then they may destruct the membrane materials. So, that is why to remove all these things we need to pre-treat the feed before it is allowed to go to the membrane module. Now, here we have a typical membrane system configuration, that the feed comes here, then we have all these filters are used for so this mechanical filters, then adsorbent filters, they are used for first pre-treating the things, and then it is heated, and then it is goes to the actual membrane module. So, these are the pre-treating system. And here comes the performance of some of the membranes for the carbon dioxide removal. So, these are some commercial membranes. So, we find that these membranes we have, and they have been done with different mixed gas and single gas, all these things. That means this is mixture of carbon dioxide with other gases, and this is only carbon dioxide, and these are the percent of the carbon dioxide in this mixed gas, and we find that these are the permeabilities given in Barrett for carbon dioxide and methane. So, that means these membranes are more selective towards carbon dioxide. So, that is why we find this selectivity is 22 to about 4%, it differs. So, we can get that these kind of membranes can be used to separate carbon dioxide from the methane. The advantages of the membrane separation are that they have low capital investment when we compare with the solvent systems for the acid gas removal. Then they are easy to operate, their installations are easy because they come in small modules, and they have simplicity of their construction, and especially because they do not involve any kind of moving part, and then they have high turn down ratio, that is the ratio between the highest to the lowest feed rate they can handle. Then high reliability and on stream time, and then we do not need any kind of chemicals, and they have good weight and space efficiency, that is they do not occupy much of space and they are not very heavy. On the other hand, these membrane systems has several disadvantages also. In this case, we find that because we need several modules, and these modules have to be connected externally by some pipelines. So, overall we find that by using the modular structure, the capital cost increases, and along with that the operating cost or maintenance cost also increase. Then we need feed pre-treatment before the mixture is sent to the membrane module. Then the gas compression is needed because the membrane can work well when we have high pressure difference between the permeate side and the retentate side. And then we have we need to remove the H2S removal, that in the H2S and carbon dioxide permeation rates are roughly the same. So, H2S specifications may be difficult to meet. That means it is difficult to separate out the carbon dioxide and the H2S separately, and cannot be used to alone to meet the PPMV. That means if we have very small amount required in the outer stream, then only membrane cannot be used, it can be added with the other acid removal process. Now, next we come to the adsorptive acid removal. Now, in this case, this is less popular than absorption, and this is getting developed also, and that at ambient temperature substantial amounts of both the gases and are adsorbed even at low partial pressure, that is both H2S and CO2 can get adsorbed at low partial pressure rho concentrations. And these are the type of adsorbents used: molecular sieve, which may be zeolitic or may be activated carbon, and we have the metal oxide, what we call metal organic framework MOF. And here we find the performance of various adsorbents. So, these are the kind of adsorbents which are used: activated carbon, zeolite, titanosilicate, etc., alumina, etc. And here we have the carbon dioxide, and we find that these are the operating temperatures for all these kinds of adsorbents, and these are the pressures of the carbon dioxide, and these are loading, and these are the regeneration method. That means, in most of the cases we find the regeneration is done by the pressure swing adsorption, and in some cases we have this temperature swing adsorption. And here we have a typical membrane separation system for H2S removal. What we find here, we have the feed gas which passes through various these beds, but mind it that all the beds are not performing adsorption at the same time. Here we have that so typical, suppose bed 1 is undergoing adsorption, but then bed 3 is undergoing regeneration, whereas bed 2 is being cooled and getting prepared for adsorption. So here we are finding these 3 beds. It may be 2 bed, minimum is 2 bed, but it may be 3 or 4 depending on the different times for regeneration, for cooling down. So in this, typically we find we are using 3 adsorption beds to carry out the H2S removal. Now when we talk of molecular sieve for removal of the acid gases, these molecular sieves can reduce it to very small amount, about 6 milligram per standard cubic meter, and they need regeneration of the bed at a quite high temperature for extended time with the potential of COS formation, carbonyl sulfide, if this kind of zeolite is used, 4A star. And here we find how H2S and CO2 get adsorbed on this molecular sieve. In here we find that this kind of molecular sieve is having more affinity towards carbon dioxide and less for H2S, though the difference is not very much, and it increases at higher gas pressure. And now we know that there are several methods for regeneration. One is the pressure swing adsorption, and there is a thermal swing. In this case, pressure swing is more common because we are talking of handling high amount of the gases. And these are the advantages of the membrane separation, that they are simple and their relative capability of the molecular sieve beds can withstand the mechanical degradation. That means they may not be getting attrition. So that means they will not form powder and they can withstand high pressure, and the possibility of simultaneous dehydration of gases and the acid removal. That means we can remove water and carbon dioxide and H2S simultaneously. Disadvantages are that there is a energy penalty for the regeneration. That means we need energy for the regeneration of this catalyst and adsorbents, and the low applicability because water displaces the acid gases on the adsorbent bed, because the water will get accumulated in the bed. Now acid gas removal is sulfide scavenger. Then these scavengers are used when the quantity of sulfur to be recovered is small, of the order of say 100 kg per day or less. So it uses small scale batch processes for H2S removal, and the scavengers are non-regenerable. That means only once they can be used because they react chemically, and these scavengers are the chemical that chemically react with the sulfur compounds to convert them to more inert form. Because they are getting chemically reacted, so it is not possible to regenerate the scavengers. So these are the desirable properties of the scavenger, that they should react completely and rapidly with the sulfides. They should be able to react in a wide range of chemical and physical environment like pH, temperature, pressure, etc. They should be non-corrosive, and they should be economically and easily available, and there should not be any kind of risk to health, to safety, and it should be environmental friendly. Now here we have a few scavengers. Some are solid based, some are liquid based. So solid based we have iron oxide, zinc oxide, and in liquid we have all these scavengers. So among all these scavengers, the iron oxide is the most common, and we have this for the this iron oxide we have the redox reaction takes place, and this is the reaction with the iron oxide, and we find that it reacts with the H2S to give this FeS2, this is precipitates, and we have water and hydrogen. And the steps involved are that removal of H2S from the gas by absorption into a caustic solution, then oxidation of the HS ion to elemental sulfur via some oxidizing agent, and separation and removal of the sulfur from the solution, and regeneration, that is oxidation of the oxidizing agent by use of air. So, these are the several steps which are involved in the scavenging of the H2S by iron oxide. And lastly, we come to some of the low temperature methods. These low temperature methods are getting developed, and there are several broad categories of these. Some are the vapor liquid mass transfer is involved, some are just some thermodynamic phase transition, and some of them are hybrid methods. So, all these methods are also getting developed, and some of them have been proposed, and like we have distillation, extract distillation, then there are solidification, cryogenic packed bed, refrigerant blend, expander. Then under hybrid we have control freeze zone, cryocell, and condensed rotational separation. So, among them we shall be talking about distillation, which is most common among the low temperature removal of these gases. So, they are good to remove both carbon dioxide and H2S from natural gas, because their vapor pressures are considerably different from the other natural gas components. And here we have the vapor pressure chart for these gases, that we find that these carbon dioxide H2S, their vapor pressures are quite different from that of the methane. And these distillation faces operating problem during carbon dioxide separation from different natural gas components. And here we have the operating problems with methane, that methane may get solidified, means results in solidification of carbon dioxide in the transmission line. So, that means if the carbon dioxide solidifies, then it will choke the flow. Then for ethane also same thing happens, carbon dioxide can get solidified, and there could be complete separation of these two by simple distillation. May not be there because it forms azeotrope. Azeotrope means we have some vapor liquid phase change at single temperature. Vapor liquid phase change we have learnt earlier, that when we have a mixture of components, then generally this vapor liquid phase change, that is either evaporation or the condensation, takes place over a range of temperature, that is the dew point temperature and the bubble point temperature, and within these temperatures we find that we get some separation. But if these components from some azeotrope, then this phase change would occur only at a single temperature, and then we will not be able to get any kind of separation. So, that is why we find that they form azeotrope and we cannot get any separation. And in case of H2S, the mixture forms a pinch at high carbon dioxide concentration. Then we have these commercially used methods like Ryan-Holmes and the controlled freezing zone process. Ryan-Holmes is quite popular, and this is a typical method, that it has an extractive distillation process that uses hydrocarbons to significantly alter the behavior of the system. The hydrocarbons are normally mixtures of propane and heavier hydrocarbons. They are obtained from the feed mixtures, and they can effectively eliminate distillation problems, and no additional separations are required. And this is a typical Ryan-Holmes process, in which we find the natural gas is coming after compression, dehydration. It is passing through several columns, and in each of the columns we are able to recover the various gases, and ultimately we are able to produce the natural gas. And here we find that we are getting the NGL, that is the natural gas liquid, and the sulfur here is obtained here, and the other gases are being recovered from this. And ultimately at the last stage we are able to get this C4 plus compounds here. So, this is a typical 4 column Ryan-Holmes process to take out the H2S and carbon dioxide from the natural gas. So, this low temperature acid gas removal have some advantages, like we do not need any kind of regeneration, they are environmental friendly and there is no corrosion of the equipment, whereas disadvantages are they are costlier due to requirement of low temperature, and these low temperatures need different types of refrigeration systems, and especially this we need to have some kind of cryogenic systems for this, which we are not talking in this particular lecture, and they are not suitable for gases having low concentration of acid gas. And here we have the references which will talks in more detail about these various processes we have learnt about the acid gas removal, that is the removal of the carbon dioxide and H2S. Thank you.